We think we know what's real. There is a floor beneath your feet. There is a chair you might be sitting on. You can knock on a table and feel the solid wood push back against your knuckles. This is the world we experience. It feels solid, definite, and reliable. We navigate it. We build things in it. We trust it. But what if this world of solid objects is just a surface impression? What if, underneath it all, reality is something else entirely? Something less solid, more fluid, and made of something we can't even see. The question is a big one. Is reality just fields of energy? Let's start with what feels obvious. For a very long time, we thought the world was made of tiny, solid bits. The ancient Greeks called them atoms, meaning uncuttable. They imagined the universe was just these tiny, indivisible balls of stuff bouncing around in empty space. A rock was made of rock atoms. Water was made of water atoms. This idea made a lot of sense. It explained why things had different properties. The atoms of a rock were hooked and jagged, clinging together. The atoms of water were smooth and round so they could flow past each other. It was a simple, mechanical picture of the universe. And for thousands of years, it was the best idea we had. Even when science got more sophisticated, the basic idea stuck around. In the 19th century, scientists like John Dalton proved that chemical reactions worked as if elements were made of discrete packets. They started to build a picture of atoms as tiny solar systems. There was a dense core, the nucleus, like a sun. And then there were smaller particles, electrons, orbiting it like planets. This was the model most of us learned in school. The atom was still a thing, a little object. A hydrogen atom was one proton with one electron zipping around it. A table was just a giant, stable collection of these tiny solar systems all locked together. The universe was still fundamentally made of stuff. It was made of particles. This particle-based view of reality works really well for a lot of things. It explains chemistry perfectly. It lets us build computers and engines in medicine. It's an incredibly useful model of the world. But it has problems. When we started to look very, very closely at these tiny particles, they stopped behaving like tiny balls. They started to act weird. And this weirdness is what cracks open the door to a completely different understanding of reality. The first big clue that something was wrong with the tiny ball theory came from light. For a long time, there was a debate. Is light a stream of particles, or is it a wave? Isaac Newton thought it was particles. Others showed it behaved exactly like a wave in water, creating interference patterns. The debate went back and forth. Then, early in the 20th century, Max Planck and Albert Einstein showed that light does come in discrete packets of energy, which we now call photons. So, it was a particle. Case closed. But it wasn't. Scientists performed an experiment that is still one of the most mind-bending things in all of physics. It's called the double-slit experiment. The setup is simple. You have a barrier with two thin, parallel slits in it. You shoot something at the barrier, like tiny pellets from a gun. On the other side, you have a screen that detects where the pellets land. If you shoot pellets with only one slit open, you get a single band on the screen right behind that slit. Makes sense. If you open the other slit, you get a band behind that one. If you open both slits, you get two bands, one behind each slit. It's just what you'd expect from tiny solid things. Now, let's do it with waves. Imagine sending water waves toward the barrier. When the waves pass through the two slits, they spread out on the other side. But now you have two new wave sources, one at each slit. As these two new sets of waves spread, they interfere with each other. Where the crest of one wave meets the crest of another, they add up to a bigger wave. Where a crest meets a trough, they cancel out. The result on the detector screen is not two bands. It's a whole series of bands, an interference pattern of bright and dark stripes. This is the signature of a wave. Here comes the weird part. Scientists decided to shoot electrons, those tiny particles that orbit the nucleus, at the double slits. They shot them one at a time. This is important. It wasn't a stream of electrons interfering with each other. It was one single electron, then a pause, then another single electron. Since an electron is a particle, a tiny ball, you'd expect to see two bands on the screen, just like with the pellets. Each electron would go through one slit or the other and hit the screen behind it. But that's not what happened. After shooting thousands of electrons, one by one, the pattern that emerged on the screen was an interference pattern. The pattern of a wave. This is impossible if the electron is a simple particle. How could a single electron traveling alone interfere with itself? It would have to somehow go through both slits at the same time, as a wave would, and then interfere with its other self on the other side before landing as a single dot on the screen. The very act of being a particle and a wave at the same time seemed to be happening. Scientists, baffled, decided to watch. They put a detector at the slits to see which slit each electron actually went through. As soon as they did that, the interference pattern vanished. The electrons went back to behaving like particles. They formed two simple bands on the screen. It was as if the electrons knew they were being watched. The act of measuring which path the electron took forced it to choose a path and behave like a ball. When you didn't look, it behaved like a wave, exploring all possibilities at once. This experiment shattered the old picture of reality. The fundamental building blocks of matter were not tiny, solid balls. They were something else. They had this strange dual nature. They were both particle-like and wave-like. This is called wave-particle duality, and it's a cornerstone of quantum mechanics. An electron isn't a ball. It's better to think of it as a cloud of probability. It doesn't have a definite location until you measure it. It's a wave of potential, and when it interacts with something, that wave collapses into a single point, a particle. This is a huge shift in thinking. The world isn't made of things. It's made of probabilities and potentials. But what is it that's waving? If an electron is a wave, what is the medium it's waving in? A water wave needs water. A sound wave needs air. What is the stuff of an electron wave? The answer to that question is the field. This is where we get to the heart of the matter. The most modern and successful theory in all of physics is called quantum field theory, or QFT. It says that the most fundamental thing in the universe is not a particle, it's a field. So, what is a field? A field is something that exists everywhere in space and time. It has a value at every single point. Think of the temperature in a room. At every point in the room, next to the window, above the heater, in the middle of the floor, there is a specific temperature. You could map it out, that's a temperature field, or think of a magnetic field, you can't see it, but if you sprinkle iron filings around a magnet, they trace out its lines of force. The field is a property of space itself. It's a condition of the vacuum. Quantum field theory says that the entire universe is filled with these fields. And there isn't just one. There's a field for every fundamental particle we know of. There is an electron field, filling all of space. There is a photon field for light. There are quark fields, there's a Higgs field, everything is a field, so where do particles come from? In this picture, a particle is not a fundamental object. A particle is just a vibration, a localized excitation in its field. Imagine a calm, flat lake stretching out to infinity. That's a field in its low energy state, what we call the vacuum. Now, if you tap the surface of the lake at one point, a ripple spreads out. That ripple, that localized little packet of energy, is a particle. An electron is just a ripple in the electron field. A photon of light is a ripple in the electromagnetic field. These ripples can travel across the field, they can interact with each other, and they can fade away. This idea explains wave-particle duality perfectly. A particle is a wave. It's a wave in a field. It's spread out like a ripple. But when it interacts with something else, like a detector screen, the interaction happens at a single point. So it also appears to be a particle. The particle is the point of interaction. The wave is the ripple traveling through the field. It's not one or the other. It's both, because a particle is just how we perceive an interaction of a field. So let's go back to the table, the solid hard table. According to quantum field theory, what is it really? It's not a collection of tiny solar systems. It's a vast, incredibly complex, and stable pattern of interacting field excitations. What you call a table is a furious dance of energy. There are up quark fields and down quark fields vibrating in just the right way to form protons and neutrons. There's the electron field vibrating in patterns around those nuclei, forming atoms. These are all held together by vibrations in other fields. The electromagnetic field provides the photons, the messengers that create the force holding the electrons to the nuclei and one atom to another. All these different fields are overlapping, interacting, and vibrating together in a stable, self-sustaining harmony. When you knock on the table, your hand doesn't actually touch it. The electron field in the atoms of your hand gets very close to the electron field in the atoms of the table. These fields repel each other. The force you feel, the solidness, is just the electromagnetic field carrying energy and momentum between your hand and the table, saying you can't go any further. You are feeling a force, which is itself just an interaction between fields. Solidity is an illusion created by force fields. You're not touching the table, you're being pushed away by its fields. This view of reality changes everything. It changes our understanding of what mass is. We used to think of mass as the amount of stuff in an object. A bowling ball has more mass than a tennis ball because it has more stuff. But in QFT, that's not quite right. Particles don't just have mass inherently. They get their mass from interacting with a specific field called the Higgs field. The Higgs field permeates all of space. Some particles, like photons, don't interact with it at all. They just zip right through it, and so they have no mass and travel at the speed of light. Other particles, like electrons and quarks, do interact with it. As they move through the Higgs field, it's like they are dragging through a kind of cosmic molasses. This drag, this resistance to being accelerated, is what we perceive as mass. So the mass of a particle isn't a property of the particle itself, but a property of its relationship with the universe-spanning Higgs field. The stuff you're made of isn't stuff at all. It's energy that is being slowed down by its interaction with a field. The discovery of the Higgs boson, the particle or ripple associated with the Higgs field at the Large Hadron Collider, was a huge confirmation of this idea. This field-based view also changes our idea of empty space. What is a vacuum? We think of it as nothingness, total emptiness. But in quantum field theory, there is no such thing as true nothingness. A field can never be perfectly still or perfectly zero. There are always tiny random fluctuations, a kind of quantum jitter. Even in the deepest, coldest, darkest part of space, the fields are still there. And they are bubbling with energy. These fluctuations can, for a very brief moment, create pairs of virtual particles that pop into existence from the field's energy, exist for an instant, and then annihilate each other, returning their energy to the field. Empty space is actually a seething, churning soup of these fleeting particles. We can't see them directly, but we can measure their effects. The Casimir effect is a perfect example. If you place two uncharged metal plates very, very close together in a vacuum, they will be pushed together by an unseen force. The reason is that only virtual particles of certain wavelengths can pop into existence in the tiny gap between the plates, while virtual particles of all wavelengths can exist outside. This creates a pressure difference from the vacuum itself, pushing the plates together. So even empty space has energy. Nothing is something. The vacuum is just the lowest energy state of all these fields, but that lowest state is not zero. So if everything is just vibrations and fields, what does that mean for us, for our sense of self? It's a profound shift in perspective. Look at your hand. It seems solid and separate from the air around it, separate from the desk it might be resting on. But at the fundamental level, it's not. Your hand is a complex pattern of vibrations in the same fields that make up the air and the desk. The up quark field, the down quark field, the electron field, these fields don't stop at the edge of your skin. They extend through all of space. You are just a localized, highly organized pattern in these universal fields. The boundary between you and the rest of the universe is not as clear as it seems. We are not separate entities moving through a static, empty world. We are part of the world's fabric. We are waves on the same ocean. The atoms in your body were forged in the hearts of long dead stars. The energy that animates you is just borrowed from these cosmic fields, organized into a temporary, complex pattern. And when you die, that energy and that matter will disperse, the patterns will break down, and the fields will go on to vibrate in other forms. The sense of being a separate, solid self is a high-level illusion, a very useful one, for sure. We need it to survive, to eat, to find a mate. But at the bottom, we are continuous with the rest of the cosmos. This also helps explain why the world of our senses is so different from the world of physics. Our brains did not evolve to understand quantum field theory. They evolved to help a creature find fruit, avoid predators, and navigate a world of medium-sized objects at medium speeds. Our perception of reality is a user interface. It's like the desktop on your computer. You see icons and folders. You click on them, you drag them. It's a simple, intuitive way to interact with the machine. But you are not interacting with the reality of the computer. The reality is a dizzying dance of electricity, logic gates, and binary code. You don't see that because you don't need to. The icons are a helpful simplification. In the same way, our perception of a solid table is a helpful simplification. Our brains create this sensation of solidity, of color, of texture, so that we can interact with the world effectively. We don't perceive the roiling sea of quantum fields because it wouldn't be useful for our survival. Our senses are a translation of the underlying reality, not a direct window onto it. The world we see is a construction, a model our mind builds, based on limited sensory data from a much deeper and stranger reality. So, is reality just fields of energy? From the perspective of modern physics, the answer is a qualified yes. This is the best description we have. The standard model of particle physics, which is built on quantum field theory, is the most accurate and well-tested scientific theory in human history. It describes the world in terms of a handful of fundamental fields and their interactions. It has made predictions that have been confirmed to an astonishing degree of precision. It seems that, at the most fundamental level we can currently probe, the universe is made of these invisible energetic fields. Everything else, particles, matter, forces, you and me, is a consequence of their behavior. Of course, this picture is not complete. There are still big unanswered questions. QFT doesn't include gravity. We have Einstein's theory of general relativity, which describes gravity as the curvature of space-time. But we don't know how to merge it with the quantum field view. A quantum theory of gravity is the holy grail of physics. It might reveal that there's an even deeper layer to reality, something from which both space-time and the quantum fields emerge. And then there's the biggest mystery of all consciousness. How does this collection of vibrating fields, this complex pattern of energy that is a human brain, give rise to subjective experience? How does the dance of electrons and quarks produce the feeling of seeing the color red, the taste of a strawberry, the emotion of love, or the simple awareness of being? Physics can describe the machine of the brain in incredible detail, but it has nothing to say about how the machine generates a ghost, a mind. This is the hard problem of consciousness. The field-based view of reality gives us the ingredients, but not the recipe for experience itself. It tells us what we are made of, but not who we are. Thinking of reality as fields of energy can be unsettling. It dissolves the solid, comfortable world we thought we knew into a shimmering, probabilistic dance. It makes us less of a noun and more of a verb. We are not things, we are processes. We are patterns of energy that persist for a time. But it can also be a source of wonder. It means the universe is not a cold, dead collection of inert rocks. It is a single, vast, interconnected, and vibrant entity. Every part of it is alive with potential energy. The empty space between the stars is buzzing with activity. The matter that makes up our bodies is not separate from that space, but an integral part of it. It suggests a kind of unity. The same fields that make up a distant galaxy also make up the chair you're sitting in and the neurons firing in your brain. Well, there's a deep and fundamental connection between everything that exists. We are all made of the same cosmic stuff, vibrating to different tunes. The world is not a collection of separate objects, but a single, immense, and complex symphony. The notes are the particles, but the music is the continuous, flowing, and ever-changing reality of the fields. So the next time you knock on a table, remember what's happening. You are not a solid thing hitting another solid thing. You are a complex pattern of field energy interacting with another complex pattern of field energy. The feeling of solid is a force, a message carried by yet another field, between two temporary collections of ripples on the vast ocean of reality. The world is not what it seems. It's something far stranger, far more fluid, and far more magnificent. And we are not just living in it, we are it.